This is class 9 physics and we are dealing with a chapter force and Newton's laws of motion. We'll just have a small recall of the previous sessions. So in the previous session we have seen about the Newton's first law and about inertia. So what does Newton's first law state? So it states that any object which is going to be in motion or any object which is going to be in rest, it will be continuing its same state of rest or motion, and unless an unbalanced force is going to act upon it. So if the object is in rest, it will be in rest, and if the object is in motion, it will be in motion. And we saw about inertia. What is inertia? Inertia is nothing but it is going to be the natural tendency of the object to be in its same state. So if it is at rest, it is going to be at rest. It is not able to change its state of rest or motion. So it cannot, the object cannot change by itself. So only if any force is going to act upon it, the object may be or it will be able to change its state of position. So you can also say that the inability of the object to change or the natural tendency of the object to resist its position or motion or rest. In today's session, we are going to see about the types of inertia and some everyday examples which are related to inertia, and we'll see the Newton's second law of motion. We'll see what is the Newton's second law also. We have three types of inertia, that is inertia of rest, inertia of motion and inertia of direction. So we know inertia is the resist and change in position of the object. So here, if the object is not able to change its state of rest by itself, then it's called as inertia of rest. And if the object is not able to change its state of motion, then it is called as inertia of motion. And if the object is not able to change its direction by its own or on its own, then it is called as inertia of direction. So all these things are going to be depending upon the position of the objects here. So now first we'll see the examples of inertia of rest. So the first example is a passenger standing in a bus leans backwards when the bus starts all of a sudden. And the second one, the fruits fall down when the branches of a tree are shaken. And dust particles on a carpet falls when we beat the carpet with a stick. So when we are standing in a bus, we are at rest. And when it is suddenly the bus is being started, what happens? We move backward and then we come forward. So you're not able to change the state of rest by yourself. And here also the other simple example is like we have the apples or the fruits in the tree. So only when the branches are shaken, what will happen? The fruits will fall down. So the apple and the passenger who is at rest will remain at rest only. So they will not be able to change their positions. Okay. Then the second one is examples of inertia of motion. A passenger standing in a moving bus leans forward when the bus stops all of a sudden, and a man who is going to step out from the moving train leans forward. So here is a picture. There's a boy who's sitting in a seat and he's wearing a seat belt. So we all wear seat belt while we are moving in a car or traveling in a car. So suppose if the driver is going to apply a sudden brake because you are moving and the driver is going to apply a sudden brake. So what happens? Suddenly you cannot come to rest, right? So you will move forward and then move backward. And then even in the bus also, you might have seen like people will get inside the bus and get down the bus while the bus is in motion also. So what happens in this case, while they're getting down, while they're getting down, they will also move along the direction of the motion of the bus for few seconds. So that is, they are not able to change their state of motion, their movement. Then very simple example also you can say. So you might have seen all the running races in our school and all. So all the boys and girls, they will reach the final destination point. But if you would have observed, even after they have reached the final destination point, they will not be able to stop themselves suddenly there, right? So this is inertia of motion. So they are not able to change their state of motion here. So this is another example of inertia of motion. The next we have inertia of direction. The water particles sticking to the cycle tire are found to fly off tangentially. So if you have a cycle in your home, if the water is being stuck to the cycle and when you start pedaling, what will happen? It will not go in the circular direction. It will go along the direction of the cycle only here. Another very simple example is, you can see here a car is moving in a curved road. So if you are inside the car, what will happen is, along you will also move along the direction of the curved path here. So suddenly you're moving straight and there is a curved path. So what will happen? You will move in the opposite direction of the curved path here. So there is the inability of the passenger or of the object to change its state of direction is called as inertia of direction. Then here I have few situations. So the first one, like what we have already seen, there's a stationary bus and the bus starts to move. What happens? You will lean for backward and then you will come forward. So these are few examples what we are seeing in our everyday life. Then the second one, it's also inertia at rest here. So what will happen here? So there is one tumbler and on top of it we have a cardboard, and on top of the cardboard we have a coin. So suddenly if I'm going to pull the card away, what will happen? The coin falls down due to gravity only, but it is in the same state of rest only. Then the third one, I have a pile of books here, and in between I am just removing one of the book also. So what will happen to the other book? They will also drop down due to gravity and they will remain in the same state. So these are few examples what we see in our everyday life. Then we have a moving bus and suddenly the driver is going to stop the bus, and what will happen? Everybody will move forward because they are already in motion, and when the bus is stopped suddenly, the passengers are also in motion here and they move forward. Now we will see a relationship between inertia and mass. So inertia and mass have certain relation between them. So we'll see what is that relation. So here you can see I have two bricks here. So one is small and one is big. Which one do you think will be easy for us to push? The smaller one or the bigger one? So obviously everybody will say that the smaller brick will be easy for us for pushing here. So what happens if I ask you to push the two bricks, which will be easy for us? The smaller brick will be easy for us to move and the larger brick, it will be a little bit tough for us. So if the object is going to become heavier, what will happen is its tendency to resist, to change its state of resist the motion will become more here. So inertia is itself, we know, to resist the change of position. So if it is a smaller object, it will be easy for us for moving, and if it is going to be a bigger object or heavier object, it will be difficult for us to move it here. So here for us, as the mass increases, the inertia also increases. That is, the resistance to change its position will be increasing. So we can say that the inertia is going to depend upon the mass of the object. So less objects, less inertia. Heavier objects, or you can say light objects, less inertia. Heavier objects, you will need more inertia or greater inertia. So we know that inertia is the tendency of an object to resist a change in its state of motion. And how do you measure inertia here? So inertia can be measured directly by mass. So you can also say that inertia has direct dependence upon the mass of an object. So we all know that mass is nothing but the amount of matter which is present in an object here. Okay, and if the object is going to have more mass, what will happen is your inertia will be more. So the inertia increases as the object's mass increases, and the inertia decreases if the object's mass decreases. The next topic we are going to see is about Newton's second law of motion. So we have seen about Newton's first law, we have seen about inertia and the types of inertia also, and the relationship between inertia and mass. So now we will see what is this Newton's second law of motion. So we'll see something about the Newton's first law and then we'll move on to the second law. So the first law, we know if the objects are going to be in motion, they'll be in motion only, and if they're going to be at rest, they'll be at rest only, and they can change their state only when some unbalanced force is going to act upon them. So now if you see, in first law, if the forces are going to be balanced forces. So if the forces are going to be balanced forces, what happens? If the object is going to be at rest, it will be in rest only. And if the object is going to be in motion, the object will be in motion only and with the same speed and in same direction. Now we will see what is in the case of Newton's second law. So in Newton's second law, what happens is when the forces are going to be unbalanced, what will happen? There will be an acceleration here. So the object is going to, I'm going to apply some force, and when unbalanced forces, they are going to make your objects move. So here, when a force is applied, there is an acceleration on the body here. And what happens to this acceleration? So this acceleration is going to depend directly upon the total force which is applied here. Okay, and the acceleration which is due to the force is going to be inversely proportional to the object's mass. So in second law, there is going to be an unbalanced force, and due to the unbalanced force, the objects are going to move, and there is an acceleration, and this acceleration will be depending directly upon the force, and it will be inversely proportional to the mass of the object. Then, so we'll see what is the second law of motion. So what is this law state we will see as the first law. So the law states that when a force acts on a body or an object, it will cause the object to accelerate, right? So if you have any object and if you're going to push that object by applying a force, what will happen? Obviously, the object will move here, and if the movement is going to create accelerate the object here. Okay, and then the larger the mass of the object, the greater the force will need to cause to accelerate, right? So if the object's mass is going to be more, what will happen? We need to give too much of force so that we can make the object to move here. So we can also write this as F is equal to ma. So this is the relationship between force, mass and acceleration, or you can also write this as A will be equal to F by m. Right? So you can also write this as A is equal to F by m. So now you can say that the acceleration is directly proportional to the force and it is inversely proportional to the mass of the object here. The Newton's second law will be talking about another physical quantity which is called as momentum here. So we are going to see what is momentum in Newton's second law here. So what is this physical quantity? It has some relationship with this inertia also. So we know inertia is the another property of mass and it is going to depend upon only on mass here, and inertia is a scalar quantity and it talks about the resistance change in position. Then momentum is going to be the property of a moving mass that resists changes in a moving object's velocity. Okay, so it's going to depend upon the objects which are moving and that is not able to change its motion here. That's the thing. So momentum is going to be nothing but any object which is going to be moving, or all the objects are going to have a mass. So and if the object is going to be moving and it is not able to change its motion, that property we call it as momentum. And here this momentum is going to depend is a vector quantity. If it is going to be a linear motion, that is any object which is going in a straight path, then that time we call that motion to be, that momentum to be a linear momentum. So momentum, linear momentum we represent as the term P vector. So this is the symbol, vector symbol, which represents that momentum is a vector quantity and it has both magnitude and direction. And particularly, as I said earlier, it is going to represent the inertia in motion. And Sir Isaac Newton also described that momentum is the quantity of motion. Only with the help of momentum we can talk about the motion of the object. So to tell in simple words, okay, what it is going to reflect the effort required to bring a moving object to rest depends not only on its mass but also on how fast it is moving. So if you see any object, like if you're going to throw one ball, okay, so as I said earlier itself, inertia is having a dependence on mass. So if you want to throw, you're going to throw a ball. So you have thrown that ball, the ball is going to be in motion. So if you want to bring that ball to rest, what happens? If it is a heavier ball, you need to give a heavier force. If it is going to be a very small, light ball, it's not necessary that you have to give a greater force, right? So if it is not only going to depend upon the mass, that is inertia, but to bring an object to rest, to bring that ball to rest, what we have to do? It will also be depending upon the motion of the object, how fast the object is also moving. Okay, this is the general application what you can say about momentum. So it is not only, if you want to bring any object to rest, it is not only going to depend upon the mass but also it will be depending upon how fast the object is moving also. So the definition, general definition of momentum is nothing but it's going to be product of mass into velocity here, and momentum is a vector quantity. The SI unit of momentum is kilogram meter per second. So mass SI unit is kilogram and velocity SI unit is meter per second. So that's the reason we have got kilogram meter per second. Here I have got an example of momentum. So suppose they are considering a boulder and a stone also. So if you see, a moving boulder has more momentum than a stone rolling at the same speed. Okay, so a boulder is moving and the stone is also rolling. So here a moving boulder is having more momentum than in case of a stone. Then we have a fast boulder has more momentum. So if you take two boulders and both are going to move in different speeds, so the fast boulder will have a more momentum than a slow boulder. And any boulder which is going to be, it is not going to be in motion at all. What will happen? It is not going to have any momentum. So your momentum is going to be talking about how fast the object is going to be moving. With the help of the physical quantity momentum, you can also state the Newton's second law of motion the other way. That is, the rate of change of momentum is proportional to the force applied to make the change and takes place in a straight line, right? So whenever you come across the word rate of, it represents at a particular time, at what time it is taking place. So momentum here is going to be directly proportional to the force of the object to make the change. So only when you are going to apply the force, the object will be moving here. So any object which is going to move, they are going to have momentum here. And that change, how it is going to take place, it will be taking place in a straight line. So this is your another way of stating Newton's second law of motion. In today's session, we have seen about the types of inertia and we have seen about Newton's second law of motion and the statement for it also. The next session, what we are going to do is, we are going to derive the mathematical formulation of Newton's second law of motion. So that's the very simple formula, that is F is equal to ma. So we are going to use the formula for momentum and we are going to derive this relation. Thank you, children.